For question 1, we need to determine the local maximum, local minimum, and or saddle points for the function fxy equals to x squared plus 5y squared plus 8x minus 10y minus 13. Using unconstrained optimization, we need to find first order partial derivative for fxy respect to x and respect to y. Then we apply second order partial derivative respect to x and y. After that, we derive this in second order partial derivative with respect to y. In order to find critical point, we need to set the first order partial derivative equals to 0. Find x and y using the equation. To find local extremum, we need to find domain by using this formula. Substitute the value into the formula. If the domain greater than 0, we need to check the value of the second order partial derivative with respect to x. If the value is greater than 0, so the critical point is local minimum. Find x and y. The coordinate is -4, 1. To find local extremum, we need to find domain by using this formula. Question 2. Determine the local maximum, local minimum, and or saddle points for the function fxy equals to 18xy minus x cubed minus 9y squared. Using unconstrained optimization, we need to find first order partial derivative respect to x and y. Then we apply second order partial derivative respect to x and y. After that, we derive this in second order partial derivative with respect to y. In order to find critical point, we need to set the first order partial derivative equals to 0. Find x and y. The coordinate is 6, 6 and 0, 0. To find local extremum, substitute the coordinate into the second order partial derivative. To find local extremum, we need to find domain for each coordinate by using this formula. Substitute the value into the formula. If the domain for 0, 0 is smaller than 0, so we consider the critical point is saddle point. Then we substitute the value into the second coordinate. If the domain for 6, 6 is greater than 0, we need to check the value of the second order partial derivative with respect to x. If the value is greater than 0, so the critical point is local minimum. But if the value is smaller than 0, so the critical point is local maximum. For question 3, we need to determine local minimum, local maximum, or saddle points for function x cos y. Using unconstrained optimization, we need to find first order partial derivative with respect to x and y. Then, we apply second order partial derivative with respect to x and y. After that, we derive this in second order partial derivative with respect to y. In order to find critical point, we need to set the first order partial derivative equals to 0. Then, we get y equals to pi over 2 and 3 pi over 2. We substitute y in this equation and we get x equals to 0 and we get x equals to 0 for y equals to 3 pi over 2. So, the coordinate is 0 pi over 2 and 0 3 pi over 2. Then, we substitute the value into the second order partial derivative. To find local extremum, we need to find domain by using this formula. If the domain is lower than 0, so we consider the critical point is saddle point. So, the critical point for 0 and pi over 2 is saddle point. Same goes to coordinate 0, 3 pi over 2. The domain is lower than 0, so the coordinate is saddle point.
Question B1. By using the substitution method, optimize x plus 2xy subject to 2x plus 4y equal to 100. So first, we let fxy equal to x plus 2xy. So from the subject, we find the x and then we label it into 1. And then we substitute equation 1 into fxy. And then we will get negative 4y squared plus 98y plus 15. And then we find the partial derivative with respect to y, which is negative negative 8y plus 98. And then we can find the coordinate of y, which is 12.25, and we label it as equation number 2. Then we substitute equation number 2 into equation number 1. Then we can get the coordinate of x, which is 25.5. So the coordinate is 25.5 and 12.25. So to find the optimization value, we substitute the coordinate at the original equation. Then we will get 650.25. Question B1. By using the Lagrange multiplier method, solve the following. Optimize the objective function, which is 3x squared plus y squared minus 2xy subject to the constraint 6 equal to x plus y. So the function given is 3x squared plus y squared minus 2xy, and the constraint is x plus y minus 6. First, we find the partial derivative of x with respect to x, the partial derivative of f with respect to y, the partial derivative of g with respect to x, and also the partial derivative of g with respect to y. Then we substitute the value into the formula of Lagrange multiplier. Then we can find the value of y, which is y equal to 2x. Then by using the constraint x plus y equal to x plus y minus 6, we substitute the value of y, then we can get the coordinate of x, which is 2, and the coordinate of y, which is 4. Then we substitute the coordinate into the original equation. Then we will get 12, which is the maximum point. For question number 2, we let the x1, given the x1 is quantity of good 1 that is bought, and the x2 is quantity of good 2 that is bought. So we let equation 1, which is u equal to x1 multiply x2, and equation number 2, 10x1 plus 2x2 equal to 100. So first we let v equal to 10x1 plus 2x2 minus with 100, and then by using the Lagrange multiplier method, we substitute the value of partial derivative of x and also the partial derivative of g, and then we can get 5x1 equal to 10 lambda. So we let 5x1 equal to x2, then we substitute the value of x2 equal to 5x1 into equation of 2. Then we can get x1 equal to 5 and x2 equal to 25. Then we substitute the value of x1 and x2 into u, which is the equation 1. Then we will get the u is 125. So the optimization value is 125 when x1 equal to 5 and x2 equal to 25.
The question given is find the minimum value of the function fxy for minus x squared minus y squared subject to the constraint g xy x squared minus 2x plus y squared negative 3 less than equal to 0. So by using the Lagrange method, so we have to use this formula. Then we find the del f, del x, del f, del y, del g, del x, del g over del y. So by using this formula, we can find the value of x and also the value of y, which is the x we found is x equal to 1, and the y x equal to 1 and also x equal to negative 0.8445, and when the x is equal to 1, so the value is undefined. When we substitute the value of x equal to negative 0.8445, the value is plus minus 0.7722. So we know that the minimum value is the value of x and also the value of y.